Imagine you're standing in an elevator, and suddenly the floor drops. Your stomach lurches upward. For a brief moment, you feel almost weightless, like gravity forgot about you entirely. That's not a coincidence. That's Newton's laws of motion at work. These laws quietly govern every movement you make, every force you feel, and every collision you witness. They connect the physical world you experience every day to precise, predictable mathematics. By the time this session is over, you'll be able to look at any moving system, a sliding block, a falling rocket, a pulley with weights, and say exactly what's happening and exactly why. To begin, here's our roadmap for this session, where we will overview the core topics of mechanics. We will start with inertia and its three distinct types, followed by the mechanics of rocket propulsion and equilibrium. Next, we build a foundation in force, linear momentum, and impulse, then continue with friction and inclined plane dynamics. Our study also includes a rigorous deep dive into all three of Newton's laws, as well as an analysis of pulley and contact mass systems. By the end of this session, you will see motion not just as something that happens, but as something you can predict, calculate, and master. So what actually keeps a stationary object still? And what keeps a moving one going? The answer is inertia. Inertia is the property of an object by virtue of which it cannot change its state of rest or uniform motion along a straight line on its own. That phrase, on its own, is everything. Notice the relationship with mass. A heavy bus has large mass and therefore high inertia. Difficult to start, difficult to stop. A light bicycle has small mass and low inertia. Easier to start, easier to stop. Greater mass always means greater inertia. And inertia comes in three forms: inertia of rest, inertia of motion, and inertia of direction. Each one gets its own treatment next. The first type is inertia of rest, the tendency of a body to remain in its position of rest. A body at rest stays at rest, and it cannot start moving on its own. The diagram makes this concrete. A body sitting on a surface, zero movement, no force applied. Two examples bring this to life. When you beat a carpet with a stick, the carpet jerks forward suddenly, but the dust cloud stays momentarily stationary. The dust hasn't received enough impulse yet to move with the carpet. That delay is inertia of rest. Second example, the tablecloth trick. Pull the cloth quickly, and the dishes remain right where they are, held in place by their own resistance to sudden motion. The dishes simply don't respond fast enough to the brief force. Inertia of motion means a body in uniform motion cannot accelerate, slow down, or stop on its own. It resists any change to its current state. The passenger diagram shows this directly. When a vehicle suddenly stops, the passenger bends forward. The vehicle stopped, the person didn't, not right away. The third type is inertia of direction. A body cannot change its direction of motion by itself. The stone diagram illustrates the point perfectly. A stone tied to a string moves in a circular path only because the string constantly pulls it inward. Cut the string, and the stone flies off in a straight line. Direction doesn't change on its own. So what actually overcomes inertia? Force. Force is a push or pull that changes, or tries to change, the state of rest, the state of uniform motion, the size, or the shape of a body. That word tries matters. Even if a force doesn't produce visible motion, it's still acting on the body. The push and pull diagram shows both in action: a hand pushing a block to the right and a person pulling that same block. The SI unit of force is the Newton, N, and its dimensional formula is mLT to the power of -2. Forces are vectors. They have both magnitude and direction. When multiple forces act on a body simultaneously, Newton's second law responds to the net force, which is their vector sum. The diagrams show two cases: forces in the same direction adding to 90 newtons, and opposing forces leaving a net 20 newtons to the right. Forces fall into two fundamental categories. Contact forces require physical contact between objects. Frictional force, tensional force, spring force, and normal force all belong here. The diagram shows all four: a block experiencing friction on a rough surface, a rope under tension pulled at both ends, a spring with a hanging mass, and a book being pushed upward by a table. Then there are field forces, or distant forces, which act without any contact at all. Gravitational force, electrostatic force, and magnetic force all act across empty space. Gravity is pulling you toward Earth right now without touching you at all. The field force diagrams show 3 examples: Earth gravitationally attracting a small object, opposite electric charges attracting through field lines, and 2 magnetic poles with their field between them. Moving on to slide 8, let's define the impulsive force. Formally, an impulsive force is a force which acts on a body for a short interval of time and produces a large change in momentum. While the contact is brief, the resulting effect is truly dramatic. This concept relies on a very short duration of brief contact, symbolized here by the stopwatch showing a tiny fraction of time. This brief interaction leads to a large change in momentum, often written as delta P. Look at the ball being struck. It experiences a massive shift in its state of motion. To see this in the real world, consider these common examples of impulsive force. First, a cricket bat striking a ball. The diagram shows the bat making impact for a short duration, while a large green arrow tracks the massive delta P as the ball flies away. Second, a hammer driving a nail. Here the yellow arrow shows the force of the hammer over a tiny interval, resulting in a large momentum change for the nail. Finally, a vehicle collision. In this impact, both cars experience impulsive forces, generating momentum changes in opposite directions at the point of contact. Here's the quantity that impulsive forces change: momentum. Linear momentum P equals mass m times velocity v. It measures the total amount of motion present in a body. The SI unit is kilogram meters per second. The dimensional formula is mLt to the power of -1. And momentum is a vector quantity. Its direction always matches the direction of velocity. Here's the key insight about mass versus speed. A slow, heavy truck has large mass and small velocity, but its momentum is still very significant. A fast, light bicycle has small mass and high velocity, but its momentum is only moderate. The slow, heavy truck wins. Stopping it requires far more force applied over time. There's simply more momentum to eliminate. One of the most powerful results in all of physics. If no external force acts on a system, its total linear momentum remains conserved. The total doesn't change, even when massive internal forces are being exchanged between parts of the system. The gun firing example makes this vivid. Before firing, everything is at rest and total momentum is 0. After firing, the bullet races forward with enormous velocity, and the gun simultaneously recoils backward. Those momenta are equal in magnitude and opposite in direction. They sum to 0. Total momentum is still conserved. One important note: linear momentum depends on the frame of reference, but the law of conservation of momentum itself is independent of the frame. Newton's laws, however, are valid only in inertial frames of reference. The golf club diagram sets this up perfectly. An impulsive force F applied over a brief time interval delta t. Impulse is the product of that force and the time for which it acts. The SI unit is Newton second, which also equals kilogram meters per second. Same dimensions as momentum. And that's not coincidental because impulse equals change in momentum. The force-time graph interpretation makes this directly useful. The total impulse for a force applied from time t1 to t2 is the area under the ft curve between those times. Since that area also equals the change in momentum delta p, computing the area gives you the change in momentum directly, without needing the instantaneous force at every point. Impulse is a vector quantity. Its direction is always in the direction of the applied force. Here's where impulse stops being abstract and starts saving lives. Airbags and crumple zones both work on the same principle. Extend the time over which a collision occurs. The diagram compares 2 cases side by side. A short-time collision with a rigid wall produces a very high force. An extended-time collision with an airbag produces a much smaller force. But the total impulse, the change in momentum, is identical in both. Increasing collision time is what reduces force on the occupants. The same physics applies in cricket. Pulling your hands back as the ball arrives extends the contact time, Same total impulse, much lower peak force. The hands feel the difference immediately. One principle, two very different applications. We've built all the groundwork. Now, the laws themselves. Newton's first law. A body continues in its state of rest or in uniform motion along a straight line unless an external force is applied on it. This law is also called the law of inertia. And here's the key insight that makes this more than a definition. Motion doesn't need a force to maintain itself. It only needs a force when it needs to change. On a frictionless surface, a sliding block would slide forever at constant velocity. No ongoing force required. Both diagrams confirm this. A ball at rest with zero net force, and a block moving at constant velocity with zero net force and zero friction. Two real examples follow. Beating a carpet separates the dust, and a sudden vehicle stop sends passengers bending forward. Both are inertia, resisting sudden changes in state. The rate of change of linear momentum is proportional to the applied force, and the change takes place in the direction of that force. Mathematically, F is proportional to dp over dt, leading to F equals k times d over dt of mv. The proportionality constant k equals 1 in both SI and CGS systems. The diagram shows mass m with velocity v and applied force F. Simplifying, F equals m times dv over dt, which equals ma. That is the equation. The second diagram confirms it. Net force F net on mass m produces acceleration a. This is the single most used equation in all of mechanics. Notice what happens when net force is zero. Acceleration is zero, so the object either stays still or keeps moving at constant velocity. That's Newton's first law emerging directly from the second. The first law is simply a special case. Newton's second law isn't a single scalar statement. It's a vector law. The three-dimensional diagram shows why. Force and acceleration both have independent components along the x, y, and z axes. The law breaks into three separate equations. The x component, force x equals dpx over dt equals m times acceleration x. The y component, force y equals dpy over dt equals m times acceleration y. The z component, force z equals dpz over dt equals m times acceleration z. Three independent directions, three equations. The key result, the direction of acceleration always exactly matches the direction of net force, regardless of how the individual component forces happen to be oriented. Two shopping cart comparisons make the second law immediate. First, a strong adult and a baby both push the same full cart. The adult applies a larger net force, so same mass gives greater acceleration. The diagram shows the larger force arrow on the adult's cart. Net force determines acceleration. Second, the same person pushes an empty cart and a full one with equal force. The full cart has more mass and therefore lower acceleration. The smaller arrow makes that clear. Same force, different mass, different result. Here's something deeper. Newton's second law is called the real law of motion, because both the first and third laws can be derived from it. The second law contains the other two as special cases, a profound statement about how fundamental it truly is. For every action, there is an equal and opposite reaction, and both forces act on two different bodies. The diagram shows this precisely. Body 1 exerts force F12 on body 2, while body 2 simultaneously exerts force F21 on body 1. The equation is F12 equals negative F21, equal in magnitude, opposite in direction. Now here's the critical warning, and this is where students consistently go wrong. These forces act on different bodies. They do not cancel each other out. You cannot say action and reaction cancel, therefore nothing moves. That reasoning is completely wrong. The forces act on different objects. They can never cancel each other. Cancellation only happens when two forces act on the same body. Four examples of the third law in action. Swimming. You push water backward, action, and water pushes you forward, reaction. That's how propulsion works. Jumping from a boat to a riverbank. You push the boat backward. The boat pushes you forward. Gun recoil. The bullet is fired forward. The gun kicks backward with an equal and opposite momentum change. A horse pulling a cart. The horse pulls the cart forward. The cart pulls the horse back with equal force. The modern version states it cleanly. Forces always occur in pairs. If body A exerts a force on body B, then body B exerts an equal and opposite force on body A. One final critical distinction. Don't confuse action-reaction pairs with equilibrium. Equilibrium forces act on the same body. Action-reaction pairs always act on different bodies and never cancel. Conservation of momentum extends beyond simple collisions. It explains how rockets work. A rocket is a variable mass system. As fuel burns, exhaust gases are expelled backward, and the rocket's own mass decreases over time. But the total momentum of the rocket, plus the exhaust, is conserved throughout. The diagram shows thrust acting forward on the rocket, while exhaust velocity acts backward, with mass m decreasing as fuel burns. The thrust on the rocket at any instant is given by F equals negative U times dm over dt, where U is the exhaust speed of the burnt gases and dm over dt is the rate of fuel combustion. The negative sign carries a specific meaning. As mass decreases, dm over dt is negative, making the thrust force positive, acting forward. Two equations govern rocket velocity. Without gravity, the velocity at any instant is v equals v0 plus u times the natural logarithm of m0 over m, where v0 is the initial velocity, m0 is the initial mass, and m is the present mass. When gravity is included, the equation becomes v equals v0 plus u times the natural log of m0 over m, minus gt. Gravity subtracts from the velocity gain. The variable reference makes this clear. v0 initial velocity, m0 initial mass, m present mass, t time, g acceleration due to gravity. The mass ratio diagram shows the physics. As fuel burns, m decreases. So m0 over m grows, increasing the logarithmic term and boosting velocity. That's exactly why multi-stage rockets shed their empty fuel tanks. Reducing dead mass improves the mass ratio dramatically and amplifies every stage's velocity gain. We shift now from motion to balance. A body is in equilibrium when the vector sum of all forces acting on it equals zero. Not reduced, not nearly zero, but exactly zero. The diagram shows particle O with two forces, F1 pointing rightward and F2 pointing leftward. For equilibrium, F1 plus F2 must equal zero. The forces must be equal in magnitude and exactly opposite in direction. If any force is unbalanced, Newton's second law immediately gives a non-zero acceleration, and the body starts to move. What if three forces are in equilibrium instead of two? Lamy's theorem handles that case. It states, if three forces acting on a particle are in equilibrium, then each force is proportional to the sine of the angle between the other two forces. The diagram shows three forces F1, F2, and F3 acting on point O with angles alpha, beta, and gamma between them. The equation reads F1 over sine alpha equals F2 over sine beta equals F3 over sine gamma. The application diagram shows a weight hung from two strings at different angles. Weight W and two tensions form three concurrent forces in equilibrium. Identify the angles between each pair, apply Lamy's theorem, and solve for unknown tensions without needing to resolve any components. The two most common forces in any mechanics problem are weight and normal reaction. Weight is a field force, the force with which a body is pulled toward the center of the Earth due to gravity. Its magnitude is m times g, where m is the body's mass, and g is gravitational acceleration. Weight always acts vertically downward. A distinction worth locking in, mass in kilograms measures the quantity of matter in a body, while weight in newtons measures the gravitational force acting on that matter. They are related but not the same quantity. Different units, different meanings. Normal reaction is a contact force. It acts between two surfaces in contact and is always perpendicular to those surfaces. When you stand on the floor pushes perpendicularly upward on you. That's the normal reaction, preventing the two surfaces from passing through each other. Tension is a pulling force. It always pulls a body toward the string, never pushes. The diagram shows a body attached to a string with tension T acting along the string. An important property: tension is a reactive force, not an active one. It doesn't initiate motion. It responds to the load applied. For an ideal pulley, massless and frictionless, tension remains constant throughout the string on both sides, exactly as the diagram shows. When a rope goes completely slack, tension drops to zero. These four force types are the building blocks of every mechanics problem. Weight acting downward, normal reaction perpendicular to the surface, tension along the string toward the pulley, and friction parallel to the surface opposing motion. Identify all four forces on every mass in a system before writing a single equation. Building on our force identifies, let's examine apparent weight in a lift. Case 1 is when the lift is at rest or moving at a constant speed, meaning the reading R equals mg. This occurs specifically when a lift is stationary or moving with no change in velocity. The free body diagram shows the upward normal reaction R balancing the downward weight mg. Consequently, the weighing machine displays your actual weight because acceleration is zero. For case 2, consider a lift accelerating upward, where the apparent weight R1 equals m times the quantity g plus a. This happens when the vertical motion includes a positive upward acceleration. As the diagram demonstrates, the normal reaction R1 must now overcome gravity to provide that upward acceleration. This causes the machine to show a value higher than your actual weight, making you feel heavier the moment the elevator starts climbing. Continuing our study of apparent weight, we look at cases 3 through 5 involving downward motion. The diagram illustrates case 3, where the lift accelerates downward at rate A, with the normal reaction R2 opposing gravity. This means the apparent weight follows the relation R2 equals m times the quantity g minus a. Under these conditions, the weighing machine shows a lower value than your actual weight, meaning you feel lighter. A simplified look at this equation confirms that R2 decreases as downward acceleration increases. In the extreme case 4, known as free fall, the lift acceleration equals g, so the reaction force drops to zero. This state of weightlessness is exactly what astronauts experience in orbit, where they are in constant free fall toward Earth. Finally, in case 5, if the downward acceleration actually exceeds g, the lift drops faster than the occupant. Consequently, the body is lifted off the scale and pushed toward the ceiling. So far, most of our analysis assumed ideal smooth surfaces. Now, for the force that dominates real engineering, friction. Friction acts at the point of contact between two surfaces and opposes relative motion. It acts parallel to the contact surface. The diagram shows the friction force arrow pointing left against rightward motion, and a magnifying glass view of the microscopic interface. Intermolecular interlocking between surface molecules. Friction isn't simply macro-scale roughness. It's actual molecular bonds forming and breaking at the contact level. Friction appears in 3 forms: static friction, limiting friction, and kinetic friction. Each applies in a different phase of motion. Static friction comes into play when a body tends to move but hasn't started yet. It's a self-adjusting force. As the applied force increases, static friction increases to match it exactly. The graph shows this clearly. Friction force rises linearly alongside the applied force through the self-adjusting region. Then it reaches a peak. That's limiting friction. After the peak, the body starts to move. Kinetic friction takes over, and the friction value actually drops slightly. That small drop is what makes a body suddenly accelerate the moment you push hard enough to start it sliding. You needed maximum force to start it. You need slightly less to keep it moving. Limiting friction is the maximum value of static friction, the friction that exists when the body is right at the verge of starting motion. The formula is Fs max equals the friction coefficient L times R, where the friction coefficient L is the coefficient of limiting friction and R is the normal reaction. Here's a counterintuitive result. Limiting friction does not depend on the area of the contact surfaces. It depends only on the nature of those surfaces, how smooth or rough they are. The two-case diagram demonstrates this directly. A block resting flat on its large face and a block tilted on its smaller face have identical limiting friction. Area changes nothing. Only the character of the contact surfaces matters. The angle of friction, theta, is the angle that the resultant of limiting friction and the normal reaction n makes with the direction of the normal reaction. As shown in the first diagram, this leads to a key relationship. The coefficient of limiting friction, mu L, equals the tangent of theta. Similarly, we define the angle of repose, or angle of sliding, as the minimum angle of inclination, alpha, at which a body just begins to slide down a plane. For this case, the coefficient of limiting friction, mu L, also equals the tangent of alpha. This leads to an elegant result. The angle of friction equals the angle of repose. This provides a direct experimental method to find the coefficient of friction. Simply tilt a surface until the object starts to slide. The tangent of that specific angle alpha gives you mu L directly. Once a body is actually sliding over a surface, kinetic friction takes over. The kinetic friction force, Fk, equals mu k times r, where mu k is the coefficient of kinetic friction and r is the normal reaction. As shown in the diagram, when an applied force moves the block to the right, kinetic friction opposes it by acting to the left. Kinetic friction has two subtypes: sliding friction, when one surface slides over another, and rolling friction, when a body rolls. A critical comparison to remember is that rolling friction is significantly less than sliding friction. It is always easier to roll a body than to slide it, which is exactly why wheels were invented. Finally, note that the coefficient of kinetic friction, mu k, is less than the coefficient of limiting friction, mu L. This confirms it is harder to start an object moving than it is to keep it moving once it is already sliding. On a rough inclined plane, multiple forces act on a block simultaneously. The normal reaction acts perpendicular to the plane and equals mg cosine theta. The component of weight pulling the block along the slope is mg sine theta. The net force acting down the slope is F equals mg sine theta minus the friction force F. The inclined plane diagram shows all these forces together. Normal reaction N perpendicular to the surface. Friction F pointing up the slope opposing downward motion. Weight mg pointing vertically down, and its two resolved components, mg sine theta along the slope and mg cosine theta perpendicular to it. Breaking weight into these components is the key move in every inclined plane problem. The acceleration of a block on a rough inclined plane is given by the formula A equals g into sine theta minus mu cosine theta. If theta is below the angle of repose, acceleration is 0 or negative, meaning the object won't slide on its own. In this situation, we look at two cases for pushing the block. To push the block up the slope, the minimum force required is F1 equals mg into sine theta plus mu cosine theta. Here, both gravity and friction act down the slope, so you are fighting both forces. To push the block down the slope, the minimum force, F2, equals mg into mu cosine theta minus sine theta. In this case, friction is stronger than the gravitational component pull, so you must apply force downward to overcome that friction. Moving forward from single object mechanics, let's examine the motion of bodies in contact. In this scenario, we focus on two bodies in direct contact on a horizontal surface. If a force F is applied directly to an object of mass m1, both blocks will accelerate together as a single unit. As shown in the diagram, the common acceleration A equals the total applied force F divided by the sum of the masses, m1 plus m2. We then look at the internal contact forces developed between the surfaces. The first expression shows the internal contact force on m1, which equals m1 times acceleration, or m1F over the total mass. This represents the resistance m1 feels from pushing m2. Similarly, the contact force on mass m1 is often labeled as an internal force. The third equation gives the force on m2, which is m2 times acceleration, expressed as m2f over the total mass. This confirms that the contact force on m2 is the push it receives from m1. Ultimately, the contact force is always proportional to the mass it directly acts upon. These internal forces exist in equal and opposite pairs, following Newton's third law within the system. Now, let's extend this logic to three bodies in contact. When a force F is applied to mass m1, all three blocks move together with a common acceleration. This acceleration is equal to the total force F divided by the sum of the three masses. We also look at the internal contact forces. F1 is the force between m1 and m2, which must accelerate both m2 and m3. Therefore, F1 is proportional to the sum of m2 and m3. Similarly, the contact force F2 between m2 and m3 only needs to accelerate m3. As you can see, each contact force only supports the mass ahead of it in the chain. The further away we get from the applied force, the smaller the required contact force becomes. Expanding on contact motion, let us examine stacked bodies, where block B rests on block A. In this first case, we apply a horizontal force F directly to the lower block A on a smooth surface. The diagram illustrates that both blocks move with a common acceleration equal to force F divided by the total mass m plus m. Because block A is accelerating, a pseudo-force F prime equals ma acts on block B in the backward direction. This inertial force represents the effect of block B being in an accelerated reference frame. This backward push tends to create relative motion, causing a frictional force F to develop between the surfaces, equal to the coefficient mu times mass m times g. To maintain equilibrium so that block B does not slide off, the inertial force ma must not exceed the maximum friction available. Specifically, the acceleration a must be less than or equal to mu times g. This inequality defines the critical condition for horizontal stability between the two blocks. Building on the previous concept, case B introduces friction between block A and the ground. Here we have two distinct coefficients, mu1 for the ground surface and mu2 for the interface between the blocks. The diagram shows force F pulling block A, while ground friction Fa opposes the motion of the entire system. To find the net acceleration, we first determine the net accelerating force, which is applied force F minus ground friction mu1 times the total mass m plus m times g. Consequently, the net acceleration is calculated by dividing this force by the total mass, simplifying to F over total mass minus mu1g. Shifting our focus to the equilibrium condition for block B, we must account for its inertial frame. A pseudo-force F prime equals mass m times acceleration acts on the top block to the left. This force tends to create relative motion, which is balanced by a developed friction, Fb equal to mu2mg acting to the right. For equilibrium to be maintained, the inertial push must not exceed the available friction. This simplifies to the condition that acceleration a must be less than or equal to mu2g. If this critical value is exceeded, the blocks will decouple and B will slide relative to A. Continuing our study of dynamics, let's analyze the motion of bodies connected by strings. We consider a system of three masses, m1, m2, and m3, pulled along a frictionless surface by an external force F applied to the leading mass. The acceleration of the entire system is simply the total force F divided by the sum of all three masses. Note that because each tension only works to pull the masses trailing behind it, the tensions decrease as we move away from the source of force. For the first string, tension T1 pulls only mass m1, so it equals m1 times acceleration, which, substituting our earlier expression, gives m1 times F over the total mass. Finally, tension T2 must pull both m1 and m2 together, which equates to the sum of those two masses multiplied by the system acceleration. Next, we examine the Atwood's machine, a classic example of a pulley mass system. This setup involves two unequal masses, m1 and m2, suspended vertically over a frictionless pulley, where mass 1 is greater than mass 2. For the heavier mass m1 descending, Newton's second law gives the equation m1g minus tension T equals m1 times acceleration. Conversely, for the lighter mass m2 rising, the relation is tension T minus m2g equals m2 times acceleration. By solving these equations simultaneously, we find that acceleration equals the quantity m1 minus m2 divided by m1 plus m2, all multiplied by g. The resulting tension in the string is given by 2m1 m2 divided by the sum of the masses, also multiplied by g. Beyond basic dynamics, this machine serves as a precision instrument to measure gravity by using nearly equal masses to slow the motion to a measurable rate. As seen in the diagram, mass m1 moves downward under gravity, while m2 is pulled upward, with constant tension T acting throughout the connecting string. Building on our pulley systems, let's explore two horizontal surface configurations. In case 2, we have a mass m2 resting on a frictionless horizontal table, linked over a pulley to a hanging mass m1. As shown in the diagram, mass m1 pulls the system downward, while the tension T and acceleration A act horizontally on m2. The resulting acceleration is simply m1g divided by the total mass m1 plus m2, and the tension T equals the product m1 m2g over the sum of the masses. Moving to case 3, mass m2 is now on a rough horizontal surface characterized by a friction coefficient mu. This setup includes a friction force mu, m2g, acting to the left, opposing the motion as illustrated. Due to this resistance, the system acceleration becomes the quantity m1 minus mu m2, all multiplied by g and divided by the total mass. Finally, the tension is given by m1 m2 times the quantity 1 plus mu, multiplied by g over m1 plus m2. Next, we analyze a complex system involving a central block M on a smooth horizontal surface, connected to two different hanging masses. The diagram shows mass m1 descending on the right and mass m2 rising on the left, which establishes the acceleration direction for the entire setup. We begin by defining the system for our fourth case, where the central block moves along the surface between two pulleys. Balancing the forces for mass m1 gives our first equation. m1g minus tension T1 equals m1 times acceleration. For the rising mass m2, we have the second relation. Tension T2 minus m2g equals m2 times acceleration. Looking at the horizontal motion of the central block M, the net force is the difference in tensions. T1 minus T2 equals ma. By solving these equations simultaneously, we find that the common acceleration equals the difference between the hanging masses multiplied by g, all divided by the total system mass. The tension in the right string, T1, is calculated as the quantity 2m2 plus m, divided by the total mass, then multiplied by m1g. Similarly, the tension T2 in the left string is the quantity 2m1 plus m, divided by the combined mass, multiplied by m2g. Moving to our fifth configuration, we examine a pulley system combined with an inclined plane. In this case, mass m2 rests on a smooth surface at an angle theta, while mass m1 hangs vertically. The diagram displays how the tension T and acceleration A relate to the weight components, specifically the m2g sine theta force acting down the slope. We begin with two equations of motion. m1g minus tension equals m1a for the hanging mass, and tension minus m2g sine theta equals m2a for the sliding block. Solving these simultaneously reveals that the system acceleration equals the quantity m1 minus m2 sine theta divided by the total mass m1 plus m2, all multiplied by g. Similarly, the tension is found by multiplying m1 m2 by the quantity 1 plus sine theta times g over the sum of the masses. Notice that the incline effectively reduces the gravitational influence on M2 by a factor of sine theta compared to a standard vertical hanging arrangement. Our sixth pulley case involves slide 43, where we examine two masses on two separate inclined planes. The demonstration shows mass 1 and mass 2 on dual inclines connected by a single string over a common pulley. We specifically analyzed the motion of two bodies placed on planes with different angles of inclination, theta 1 and theta 2. The common acceleration A equals the quantity m1 sine theta 1 minus m2 sine theta 2 multiplied by g, all divided by the total mass m1 plus m2. For the string tension, we multiply the product m1, m2 by the sum of the sines of both angles, times g, over the combined mass of the system. In this setup, both masses have gravity components pulling them along their respective slopes, where the net driver is the difference in these components while the inertia is the sum. Note that the specific values of theta 1 and theta 2 define the gravity components m1 g sine theta 1 and m2 g sine theta 2 that determine the motion. To summarize our study of pulleys, let's consolidate the core strategy for solving these problems. We can introduce a master pattern that applies to all pulley cases. First, remember that acceleration always equals the net driving force, or the difference in gravitational components, divided by the total system mass. Regarding tension, the value will always fall between the two gravitational force magnitudes in the system, serving as a quick sanity check. It can never be larger than the bigger value, nor smaller than the lesser one. When approaching a new problem, follow these 4 steps. Identify all forces. Draw separate free body diagrams. Write Newton's second law as sum of forces equals mass times acceleration for each mass, and solve the simultaneous equations. As an exam note, these connected mass configurations are frequently tested, so practice this workflow until it becomes automatic and fast. With that, we have truly mastered the laws of motion. Let's look back at this prescribed closing summary of our journey. We have covered the fundamental master patterns, we explored inertia, Newton's laws, and the mechanics of friction and pulley systems. These fundamental tools explain every moving thing around you. When you practice the numerical setups, you will find that everything clicks. Remember to follow the flowchart for every problem. This summary marks an important exam note for your revision. Stay curious, and we'll see you in the next session on